In a previous video, we talked about linear regression. In this video, we're going to talk about nonlinear regression. Our objective: find the equation of the nonlinear regression curve for a given set of data using the Desmos graphing calculator. Okay? So what do we know? Well, we learned in the linear regression, we learned what a scatter plot is. A scatter plot is a graph of plotted points, x's and y's, used to show the relationship, if there is one, between two sets of data. Okay, let's recall about the linear regression, whereas a linear regression attempts to describe or to model the relationship between two different quantitative variables when the relationship appears to be linear. Okay, a nonlinear regression attempts to describe or model the relationship when the relationship appears to be nonlinear or curved. Okay, so if you plot your points in a scatter plot and they look like they form a line, we're going to go with a linear regression. But if they look like they form a curve, and there are a variety of curves, then we're going to go with a nonlinear regression. The most popular curves, or the most popular nonlinear possibilities, include exponential, logarithmic, and quadratic. Okay? As with linear regression equations, nonlinear regression equations allow us to make predictions for other values. Now, in the linear video, I showed you an example. We used height versus weight of humans. Let's do some examples of the variety of possibilities that are nonlinear in these three categories: exponential, logarithmic, and quadratic. Okay, so exponential growth. A good example of exponential growth, and again, I'll just make a quick first quadrant, and the x-axis is going to be time. It'll be time for all of these examples, and the y-axis is going to be number of cells after conception. Okay, so we know when a child is conceived, you have one cell. When the sperm meets the egg, you have one cell. And then as time increases, the number of cells, they split. They grow dramatically. They grow faster and faster. So it's going to look something like this, okay? Kind of exponential growth we've talked about previously, okay? So again, as time increases, in this example, okay, the number of cells increases faster and faster. Okay, that's exponential growth. You could also have exponential decay, start off high and then come down low. That's also exponential growth. It's just exponential decay. It's a form of exponential growth. In Desmos, we're going to come up with this nonlinear equation using y1, using the equation with, again, that tilde. That tilde indicates to Desmos that we wanted to find a best fit, a regression line. And then a times b raised to the x sub 1 power. Okay, now let's take a look at logarithmic growth. Okay, again, I'll draw a simple first quadrant. And on the x-axis will again be time. So as time is increasing, this is a very general, it's not a perfect example, but you get the idea. The height of a child, okay? So basically, a child starts off pretty short when they're born, and as they grow quicker and quicker, but it begins to level out, okay? Now, yes, I realize there are growth spurts in here, etc. But in general, children's growth starts off quicker, and then as they get older, it begins to level out. And after about the age of 15 or 16, maybe 17 for boys, you kind of only, your growth is kind of done. And as time goes on, you're not growing any longer. So that's an example of a logarithmic scatter plot, or a logarithmic situation. Again, I'll put this in words. As time increases, a child's height initially increases quickly until, I shouldn't say the word until, but eventually, I'll put but, eventually levels off. And again, this is not a perfect example, but a general idea. The children will grow pretty quickly in the beginning. Once they get past their early teenage, maybe mid-teenage years, their growth essentially levels off. That's logarithmic growth. In Desmos, we're going to come up with a logarithmic regression equation using y1 tilde, and we're going to have a plus b times the natural log of x sub 1. So that'll give us the regression equation for a logarithmic curve. Okay, for quadratic situations, there are two possibilities that you run across that are popular. One possibility is you have an increase and then a decrease. Let's take a look at an example of that. And again, there's our first quadrant diagram, and we'll put time on the x-axis. And my y-axis is going to be the height of a thrown ball. Okay, so what do we know about the height of a thrown ball? Well, it starts off low, it goes up, and then it comes back down. For those who remember a quadratic graphs as a parabola. This is a parabola, it's a parabolic shape, and it's a parabola that opens down in this case. And again, this makes sense. You throw a ball, it leaves your hand, it goes up, it hits a maximum, and then it comes back down, and if no one catches it, it then hits the ground, okay? So again, let's describe this. As time increases, okay, in this case, again, as the numbers on the x-axis increase, okay, the ball's height initially increases, okay, ball's height increases, it then reaches a maximum, and then decreases. That is quadratic, a quadratic situation that data can follow. Using Desmos, okay, we're going to do a y sub 1. We're going to use that tilde again because we want it to find a curve of best fit, in this case a quadratic curve for this data. And we're going to have to use a times x sub 1 squared plus b times x sub 1 plus c, because ax squared plus bx plus c is the equation of a quadratic. Let's do the other example with a quadratic, and that is when you have a decrease followed by an increase. Okay, again, I will draw a first quadrant. I continue to use time on the x-axis. In this case, my y-axis is going to be the value of a classic car. Okay? And think about this. When you first buy a car, they start off expensive. Okay, a car's value then decreases over time. But if it's a classic car, it'll reach a bottom and then it'll begin to increase. Okay, so like 1940s Fords or something. I'm not a car aficionado, but there are certainly older cars that have become classics and their value will begin to increase. Okay, so this is an example of a quadratic situation in which you have a decrease followed by an increase. Again, the graph of a quadratic is a parabola. This is a parabolic curve, and in this case, it opens up. Okay, let's put that down in words. As time increases, the value starts off high when you first purchase a car. Okay, it then drops to a minimum. Okay, and then it increases. And again, we're looking here at a classic car. You know, someone's held on to it, taking good care of it. It's become something people want, perhaps because not many models were made or the company went out of business. And so it gets defined as classic and it starts to see its value rise. Okay, again, this is also a quadratic. So Desmos will use the exact same quadratic equation with the tilde to find the best fit nonlinear regression model. So for Desmos, y sub 1 tilde a times x sub 1 squared plus b times x sub 1 plus c. Okay, let's do an example similar to what we did with our linear regression. Let's take this off my clipboard. All right. So we want to find a logarithmic regression model for the given data. And then we want to use this regression equation to predict the y value when x is 7. You'll notice in this example, they've told you what regression model to use. That's not always the case. Sometimes you need to plot the data and make the decision for yourself. So obviously if you plot data and it tends to have an open quadratic curve or parabola like this one, you're going to want to use this equation. Okay? If you plot the data and you see it starting low and increasing faster and faster, you're going to want to go with an exponential model. Okay? But in this case, they're telling you, and we'll see it in the data, that we're looking for a logarithmic model. Okay, let me keep that up here so you can see it. Let's bring in my, my Desmos, if I can get my iPad to kick in. Okay, so here we are. Okay, because we need to put the data into this, of course. I think I've got myself straightened out here. So we're going to go back to the plus, and we're going to select a table. And so in row 1 here, we're going to put the data in. Let's see, an x of 1 corresponds to a y value of 2. The next row, an x of 4 corresponds to a y value of 9. The third row, an x value of 8 corresponds to a y value of 11. Continuing row 4, an x value of 12 corresponds to a y value of 14. And you can see over here, you know, again, Desmos has already started plotting. I'm looking at the basic Desmos screen here, and it's already showing me the points. And my last point has an x value of 16 and a y value of 15, and it happened to fit on my screen. Okay, so let's see if we have the table. If we come over here and just look at the graph, you can see. Okay, it does appear that this has started off growing very quickly, and then it begins to kind of level out. You know, you can from here to here it went from 14 to 15, whereas from here to here it went from 2 quickly to 9. Okay, so it, the spaces between are fairly consistent. This is a 3 followed by a 4, 4, 4, but we're growing rapidly, and then the growth is kind of slowing down, giving you this kind of logarithmic curve that starts off quickly and then levels out. So we want to use, so I come back into here, let me come down to here, we want to use our logarithmic equation here, our logarithmic Desmos with the tilde, because we want it to give us the best fit curve, the best fit logarithmic curve to fit this data. Okay, so I will go into row. Oh, let's first get my. Let's first press this the double arrows here, and get that section open. I'll go into row 2, and my data is in x1, y1, the table. So y sub 1. Go to the tilde, which is in the keyboard, bottom row. There's the tilde, and our logarithmic equation to come up with it is a plus b. I gotta find the b, okay. And then I want the natural log. I'm gonna go into functions, and under miscellaneous, I see the natural log is right there. I want the natural log of x sub 1, and I'll close the parenthesis. And you can see what Desmos did is it recognized that this data had a logarithmic field to it, and it plotted using least squares regression, a lot of math. It did a lot of math behind the scenes and came up with the best fit curve, the best fit logarithmic curve. And what they're telling you down here is the best fit curve is a y equals, well, a is the value of 2, or we'll call it 2.08. So when a equals 2.08 and b equals 4.65 to the 100th, that is the equation of the best fit curve. Okay, so let's write that down. Okay, so it told us that our regression model is y is equal to, okay, remember it was a plus b times the natural log of x. Okay, so we're gonna, just a second. So we're gonna say the a it told us to the nearest 100th was 2.08 plus b, which to the nearest 100th was 4.65 times the natural log of x. So this is the particular curve, the particular logarithmic curve that best matches this data. Okay? So now, okay, this of course came from Desmos. It came up with the A and the B, and it gave us the specific curve that best matches the data we have here. So now let's use it to predict what happens when x is 7. Okay, so when x equals 7, okay, we'll say, all right, well, here's the line of best, here's the curve of best fit. So we're going to put in y is equal to 2.08 plus 4.65 times the natural log of 7. And forgive me, I haven't done this in advance. And so what does this come out to be? 2.08 plus 4.65 natural log of 7. This is saying that the y value will be 11 point, and I'll do to the 100th, 13. Okay, and so interestingly for 7, it gave us a value slightly higher than 8. Okay, well, it looks like that maybe the 8, again, this is the best fit. And so it best fit with this data, and it's turning out that, using this equation, 11.13 would be our prediction. If you take a look at this on the curve, you can see here at 7, right here, it actually is a slight bit higher than 8. This curve is saying that the 8 was slightly low from the best fit. This one was above, this one's above, this is slightly low. So 7 turns out to be just a little bit higher. And that's totally okay. So there you have it. Desmos doing all the work for us to come up with the regression model for both lines and curves. And then once we have that regression model, we're able to use it to make predictions.